That's it. Yeah.
Okay, so let's get going.
Great.
So, in order to use Catlab, you start out with using Catlab,
Okay.
and I guess this kernel will take a little bit of time to start up. Um, but so have you used Julia before?
I used it for a project like a year ago, so I have some familiarity. It'll come back quickly, but yeah, I have a sense of how multiple dispatch works, a loose idea of how the macro system works, and generally everything from Python, I assume, just sort of carries over. So
Yeah.
that's my background.
So the nice thing about Julia, unlike Python, is that the multiple dispatch system makes it so that you don't really have to worry about clobbering method names.
Hmm.
So unlike Python, when you like import something, where or in this case you use using,
Hmm.
um, all of its functions come into scope. So you don't need to do like catlab dot whatever.
Okay.
Um, and so something to be generally aware of in Catlab is that so there are a lot of libraries in Julia just have one using statement.
Hmm.
In Catlab, there are a lot of different modules, and we've actually made a conscious decision to not have them always imported.
Hmm.
So, um, so for instance, if I were to import catlab.theories, then I wouldn't be able to make this definition because category is already in Catlab. But because it's all split apart,
Hmm.
um, basically what I'm doing is I'm taking some stuff that's already in Catlab and just defining it on the fly to show how you would do it. And I'm also defining it in a slightly simpler way, for illustrative purposes. But this is to show that what what I want to sort of show is that there's a core of Catlab which is actually pretty intense. Like there's a lot of macro stuff going on. There's some high power Julia going on. And then but a lot of Catlab like you could have written yourself once you understand the core.
Okay. And that's kind
So
of cool to be able to learn the core enough to formalize a new category, or is that what our goal for today is? Or
well, we're not going to formalize a new category, but it's not going to be a new category. I mean,
sure,
it's
yeah,
gonna,
yeah, yeah.
but yeah, and so the important thing is that it's not really formalizing it. We just want to be able to use it.
Okay.
Um, and you'll see exactly how we use it.
Mhm.
So anyway, so at theory is the macro that's sort of at the heart of Catlab.
Mhm.
At theory is how you declare a GAT. So a GAT is a generalized algebraic theory. And there are three types of things that can appear in a GAT. The first type is types,
Mhm.
and types can be indexed on other types.
Mhm.
That's where the generalized algebraic theory comes in. So, and you need this in order to do categories because um, a, a homomorphism has a domain and a codomain, and you can only compose two morphisms when the codomain of the first morphism is the domain of the second morphism.
Mhm.
And so the second type of thing in a GAT is term constructors. And these allow you to create terms in um, in the GAT. And then finally, the third type are axioms. But so, like I said, Catlab is more about using things and less about formalizing things. So eventually, we want to be able to do things with the axioms, but right now they don't really come into play very much.
Okay. And so is it kind of like an inductive type where for any term of this category, I can say, well, it's either an ID, like it was constructed by one of these constructors?
No.
Okay.
So that's a good question. Um, so typically when you have an inductive type, that inductive type, like if you think of like in Haskell, you have the generalized algebraic data types. The actual data type that the generalized algebraic data type generates is the initial model of that theory. And it's the initiality that allows you to decompose any term as one of the constructors.
Okay.
But so of course there's an initial category. It's the category with no objects and no morphisms, and because there's actually no way of constructing an object here.
Yeah.
And then if you have no objects, you can't construct any homomorphisms. So it's a good thing that you can't decompose any object as
Can't just do that for an arbitrary term. Okay, cool. So yeah, this definition of category makes a lot of sense to me, and the syntax sort of makes sense. What's the turnstile supposed to mean?
So it means, like, in context, A is an object, B is an object, C is an object.
Okay, and yeah, how do I type that just for convenience?
How do you type that? Well,
copy and paste it. But
so in Emacs, you can do -v.
Okay.
And that's what it is in LaTeX. I don't actually know how to. I just copied it and pasted it into CoCalc. I don't use CoCalc very much.
Okay.
Yeah, it also may be a shorthand for something. There may be like a long form version of this. I should probably ask Evan. I don't actually know.
All right. Cool. All right. So we defined a category.
So we defined a category.
It seemed like you did something with the braces right after you wrote category. What's that? Like I see
What's this?
the braces of ob and hom. Like you declared the type constructors twice, it seems like.
Yeah. So this comes into how sort of the internal machinery works, where basically so I think this will make sense when we talk about instances.
Okay.
So let's just skate over that for now.
Good.
So so we're going to make an instance of a category, or we're going to make the category of finite sets. And a finite set is just a wrapper over an integer. And a homomorphism of finite sets has a domain, a codomain, and then values, which is just for each, it's a vector, and at index I, you have f of I.
Yeah.
And so, like I said, we're not formalizing category theory, we're using category theory. So there's no sort of type constraint on values that says this is true.
Mhm.
But whenever we construct a finite set a fin set
Mhm.
we just manually check that this is true by
Cool.
checking that the length of the values is the domain,
Mhm.
and then we check that each value is within the codomain. And so one thing to note
Mhm.
for all you normal programming language users, Julia is one indexed.
Oh, wow. Okay. Yeah, that'll take some getting used to.
So so here instead of 0 less than or equal to y less than codomain.m, we have 1 less than or equal to y less than or equal to codom.m.
Okay.
So yeah.
All right. And yeah, so I see now you're plugging in those two things as the category.
Yeah. So now so okay, so let's actually run this. So now we're actually going to make an instance of the category.
Mhm.
Um and uh basically this is just a thin wrapper over Julia's native method dispatch system.
Mhm.
So under the hood, this macro generates abstract types for um, for the uh, the projections out of parameterized types and the term constructors. So does that make sense what I mean by projection out of parameterized type?
Uh, yeah, I mean, well, it makes sense in the context of like Julia thinks that vector 3 of bools is a different type from vector 2 of bools. Like it creates a different type for uh, the different like HOM AB and HOM BC are instantiated as different types.
So that's not actually true.
Okay, then I don't.
So all homomorphisms are actually the same type.
Okay.
Um, and that's where this type hom comes in here. Um, and the reason for that is that only certain things can be type parameters in Julia.
Mhm.
Specifically, anything mutable cannot, or anything heap allocated cannot be a type parameter. So if our objects were like large enough that they were going to be heap allocated, which that's actually all the time we're going to have objects that are heap allocated. They
Mhm.
can't be type parameters.
Okay.
So instead of there being type parameters, um, we just have a sort of global type of all HOMs,
Mhm.
and then we have two functions. DOM goes from HOM to OB, and CODOM goes from uh, HOM to OB. And when we declare an instance of a category, those we have to define these two functions.
Okay.
Uh,
So what did you mean by projection then?
so just like if you have um like you can sort of think of this as like a dependent sum. Do you know what I mean by dependent sum?
Yeah, yeah.
Yeah,
Uh,
so
so,
you have like the type of all HOMs
mhm.
is a dependent sum over pairs of objects and then all of the HOMs between those objects.
Sure.
Right? So
Yeah.
the first projection out of that takes a HOM and gives its domain and codomain.
Okay.
And then you can further split that into domain and codomain.
All right. Yeah. That sort of feels like specializing Well, okay, so that makes sense. Now, I guess what do you mean by types of the term constructors? Like, I think of term constructors as functions that have a type, but it sounded like you were saying term constructor
Yes.
itself is a type.
So, right, because not all theories have an idea of a function type. Like, okay, so maybe it's kind of like not all categories have internal hom.
Hmm.
Not all theories, you can't type the term constructors in all theories. Like, we're used to working in Cartesian closed categories
Hmm.
where functions are objects. Yeah, famously in Haskell, like functions are data.
Yeah.
Um, in in the in this compose and ID, they're just operations that you can do that are like they're like function symbols from a logic perspective.
Hmm.
So yeah.
So now, yeah, now that you've laid the groundwork, can you repeat again what the machinery of the instance macro did?
Yeah, so the machinery of the instance macro, it really doesn't do much. All it basically, it's just a slight wrapper over the um built-in Julia multi-dispatch system.
Hmm.
Um, I think it may it may check that you've defined all of the methods.
Hmm.
Um, it may do something else. I don't know. If it does something else, it's not particularly important.
But yeah, the theory was defining an interface, and an instance is implementing the interface.
Right.
That
But
feels very natural. Yeah.
yeah,
Uh,
but because Julia is like very dynamic, like none of this is, it's not really statically checked.
sure.
It's just like a convenient way of organizing code.
We can still shoot ourselves in the foot by declaring the compose function as f.codon or something.
Right,
Yeah,
exactly.
but okay. No, that's good to know. Uh, okay, so everything makes sense up to cell 6.
Okay. Um, okay, and this definition of ID makes sense. Um, collect just turns, so this is like a range object,
Mhm.
turns that into an actual vector. Um, and then compose, yeah, so the codomain has to be equal to the domain
Mhm.
here. And then the composed function has domain, the domain of F, and codomain, the codomain of G. That makes sense.
Mhm.
And then this expression here is pretty obvious. Um, uh, the the value for I in the domain of F is literally like G of F of I,
Yeah,
pretty much.
cool. Yeah, no, that's very, very clean. So that makes sense. So we've defined what a category is in one particular category.
Yeah. Oh, and actually, something that I didn't think to add, but is just a cool feature of Julia.
Mhm.
We can actually do f fin set hom I int equals f dot values sub I. And this allows you to override function. This allows you to override function application. So
Mhm. I see.
now down here, let's actually define that instance. So that's running. Every time you first run a Catlab macro, it takes a while.
Yeah.
Because yeah, that's how Julia works the first time you run things.
Mhm.
But anyway, so now let's make all of these, and if we make another cell, you see that using this overload, we can do f of say 1, and that's 4, which is just a kind of a cool feature of Julia. That's
Yeah.
not Catlab. That's just Julia being cool. Anyways, now you can see that we have we can define the composition of two functions. Yeah, this is all not so exciting, but like you can see, okay, now we can actually apply that. Okay, so now let's get to something a little bit more interesting, which is fin set span. Oh, do I want to do an X? Do I want to have you do something?
It disconnected me due to inactivity.
Oh, really?
And then
Okay.
I'm back now.
Okay. Yeah. Why don't you play around with this for a second? Make this do something interesting.
Okay. I guess I could try to define, let's see, is f invertible? Yeah, so f is invert. I could do like define the inverse of f, and then I don't know. Let me try that. So how do these cells work? So can I say like f inverse is going to be, I mean like the right inverse, is going to be a fin set on, and it's going to go from B to A. And so the fourth thing has to go to 1. The second thing has to go to 2, and the first thing has to go to 1, and I can do whatever I want for the third.
The third thing has to go to 3.
Well, nothing mapped to 3.
Oh yeah. No, you're right.
So let's just send that to 1. So let's see. If I'm looking at A, 1 went to 4, which now goes back to 1. 2 goes to 2, which okay, 2 goes back to 2, and then the 3 went to 1. So okay, now I think I've done it right. And this one, everything could be anything. So I've defined the inverse of f. And now if I do compose f inverse, and I apply that to 1, I should get 1. And if I do, I forget how to do this range thing.
Oh, well, here, ready?
I want to map that over the domain and just get 1, 2, 3.
Well, this is how you map things in Julia. Check that out.
All right. That's pretty cool. All right.
Yeah.
So wait, mapping is the dot syntax, or?
Yeah, that's why Julia is better than Python.
Cool. All right. So was that cool enough?
Yeah, that was cool. All right. Good. Yeah, so I hope you're sort of getting the impression that, you know, Catlab is it's not magical. There's a you know, it's just like Julia stuff that you're putting together in a way that's influenced by category theory. There's no real magic type theory stuff going on.
Okay.
All right. But you can do some pretty cool things with this. So for instance, this struct represents a span in FinSet. So you have an apex, and then you have 2 legs, which are yeah, FinSet HOMs. In order to make a span, you pass it in an apex and 2 legs, and then it just checks that the apex is actually the domain of the 2 functions. Um, and now you can construct the product of two finite sets, and okay, well, the product of two finite sets, well, you could say, okay, that's just the finite set where uh that's just the multiplication, but you actually also care about the projections. So you want this to be a span.
Mhm.
Um and the way this works is yeah, so you calculate the length. Well, it's just going to be the actual numerical product of the two finite sets.
Mhm.
You make an apex, and then you do the standard trick for mapping uh, two-dimensional indices into a one-dimensional indice. Mapping a one-dimensional index into a two-dimensional index.
Mhm.
Which is you use modulus, you use remainder and division.
Hmm. Okay. I haven't seen this. I would think that you just. Oh, okay. Yeah.
Yeah, it's like
Yeah.
it's
Yeah.
like you're putting them in a in a square box.
Okay.
Um, and then you just make the span
Mhm.
of these three things. So let's evaluate that, and we can take the product of a and b. And yeah, so, and here, let's .apex.n. We can verify that this is 12. And then if you look at the actual morphisms, yeah, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4.
Mhm.
So you see, like, okay, the first element is 1, 1. The second element is 1, 2. The third element is 1, 3.
And so how do I use this product? Like if I wanted to map F over the first, like, do F times identity as a morphism applied to this, and I get something in BB, uh, like how do I use the product? Because printing
So
out,
so that's a good question. So you want F.
like the morphism F times.
So there's another thing, right? So when you there's product in Catlab, and product in Catlab actually has two components. It has the product, which returns the span, but then there's also the universal property of product,
Yeah,
which
exactly.
which means that if you have a map into A and a map into B, then you can get a map into the product of A and B.
So this function knows nothing about the universal product. The
So
uni-
yeah, this function knows, but the universal product, the universal property is not actually that hard to implement. Like, we could just write a function, universal property, that takes two finite set homs, manually check that they, like, one goes to A, one goes to B,
Mhm.
and then returns a finite set hom to the apex. And that's implemented in Catlab. I didn't implement it here,
All
but
right.
I think you even with your current knowledge could implement that function.
Yeah, so there's no inherent CATLAB constructions for universal properties. It's
There
just,
are,
oh,
but you could implement them.
but I mean, like syntactically, they are just
No,
functions.
no, no. Syntactically, they're not. Yeah,
Okay, cool.
yeah. I mean, that would be cool. I love adding macros. It would be cool if you had like a universal property macro,
Yeah.
but yeah, we don't have anything like that yet.
All right.
Um, I don't even know what the right, like, way of thinking about that would be.
I
I don't
mean,
know.
it's like yeah, it's just like the initial object in some category, or I've heard like that's what a universal property is, or
Yeah,
uh,
yeah. I don't know.
okay, but cool. So we've got products, uh,
Yes.
fin set.
Yeah, and you can imagine, like, all of the other limits you could compute in a very similar way, just like, down and dirty.
Mhm.
You just compute them. Um, and of course, and so in Catlab we have generic code that does all of the different limits.
Mhm.
Um, and of course we do it in a more general way than this product, because you have to do it more generally to cover all the cases. So we have sort of like a data structure that represents an a diagram,
Mhm.
which is literally just like a graph where each vertex has an associated object and each edge has an associated morphism. um and then like one way to take a limit is to you take the product of all of the objects and then you filter it, like literally use the function filter.
We'd we'd call that brute force, right?
Yeah, but you can brute force the object, and I think we also have a couple more sophisticated algorithms for it.
I guess, yeah. So I imagine if I wanted to define the product in FinSet, I could do it two ways. I could find a general category, like maybe you can't, I define the product for maybe a more general type of category, and then I could say FinSet is an instance of that type of category. Or I could define it directly on FinSet, and maybe I can do it more efficiently for the more specific case. So is there like some sort of like inheritance thing where it's like, oh, I'm going to use the most specific definition that I have for this category,
so
for this?
the inheritance that we have is Julia inheritance.
Okay.
So so we have like we have sort of a general framework for sets, which include um Julia types,
Hmm.
Julia types along with predicates. And again, like it's literally just a struct, which is a Julia type and a predicate on that Julia type.
Sorry,
And then
predicate.
you're just sort of manually asserting that any function
Hmm.
between these two types preserves that predicate.
So there's a type of predicates in.
Yeah, a predicate is just a function from the type to bool.
Okay. And so,
Um,
yeah, there's no inner structure to predicates.
yeah,
There's no logic going on.
yeah. There's no logic.
Okay.
Um, and then there's finite sets, and finite sets come in a couple different flavors. There's the finite set which I talked about here, where it's just a number, and then there's like a finite set where it's actually like a data structure, which maybe contains like symbols or whatever in it.
Yeah, this implementation of finite sets just assumes there's a canonical set for each cardinality, and
Yeah,
I guess this gets into the distinction that I've heard you talk about before of like combinatorial structure versus data, like the.
yeah.
So I'm.
You were paying attention.
Yeah. So this is a combinatorial fin set, and then there's a data fin set defined
Right.
differently. I don't want to make you jump the gun, but yeah, it's uh, is it less straightforward to define the one that uh, is the data-based one?
So there's a difference between a fin set that is like a fin set that's a set of symbols is still like a combinatorial set. It's just a combinatorial set with different names.
Yeah.
A data set would be a finite set along with a morphism from the finite set into some other object. So like a finite set along with a real number for each set or a symbol for each set. The difference is that in the combinatorial thing, we're just using our names for each object as like opaque handles. Like the names don't have meanings themselves. But in so if you're calling one thing A and the other thing B, well, you could just as well call one thing B and the other thing A.
Mhm.
But if these things represent people and you don't want to confuse Mr. A with Mrs. B.
Mhm.
Yeah,
Okay.
that's the difference. But that was a bit of a sidetrack. And anyways, so this sort of instance, this is one way that we use the GAT structure. The other way is there's you can make sort of free categories.
Mhm.
And free categories are just built out of syntactic objects. So in order, before you define a free category, you have to sort of define what syntax tree it's going to use.
Uh, just off the top of my head, if we don't have axioms doing anything in GATS right now, aren't all categories free? I mean, this is my loose understanding of freeness as like not
Well,
constrained by any axioms.
not at all. I mean, because even though we don't have axioms for FinSet,
Mhm.
um, uh, FinSet is not a freely generated category.
I see.
It's just that we aren't enforcing the axioms. And yeah, I mean, we could just write down the axioms. Like the axioms are just documentation.
Yeah. Yeah.
And eventually we want to do rewriting. And yeah, if you can get us to do rewriting, that would be great. Yeah, you're gonna make the axioms mean something, right? Right, Chris?
That's the goal. But okay, so the free category uh, uh, here. So yeah, now I need to understand what's going on here. So this is the first time we've seen the syntax macro.
Yeah. So at syntax declares a syntax tree, and yeah. So the way this is a little bit janky. So if you actually dump free category,
Mhm.
dump is like a very useful Julia function. It
Mhm.
basically gives you like what things are under the hood.
Yeah.
Free category is actually a module.
Okay. Like catlab.gat is a module.
Right.
Okay.
So this like
That.
this declares a module, and inside the module are types
Yeah.
for like an object, and an object is basically just uh um it's basically just a symbol, a wrapper around a symbol.
Mhm.
And then a hom is basically just a wrapper around a symbol and then two objects.
So yeah. So I'm looking at that definition, and and I'm not yet fluent enough in Julia to know like what's in scope or not in scope. But you could have replaced hom with hom prime, or or is it inheriting hom from the namespace of category?
It's inheriting from the namespace of
Okay.
category.
So it knows to take any type. I'm just trying to think what does it how does it know what to say is a wrapper for a symbol? It looks at category and it says any type constructor there should
Yeah.
do that. Okay.
Yeah. And so just like when I put finset hom here,
Hmm.
and ob hom here, I'm putting uh ob expression and hom expression here. And that actually says that the type that I'm going to generate in this module should subtype ob expression and should subtype hom expression. And I've declared
Hmm.
uh, these up here. So now let's actually get into what this kind of thing looks like.
Hmm.
And the way that you use the syntax is via presentation. So a presentation takes in uh, a a syntax, and we're going to present the category C. The category C has 3 objects, A, B, and C, and then 2 morphisms, F and G. And this is going to run for a little bit. Okay. And now we can see what this actually produces. What this produces is a presentation. So presentation is just a struct, which contains a reference to the syntax module. And then it also has each type in the, it has a map that sends each type in the GAT. So in this case, objects and HOMs, to a list of the generators of that type. So in this case, A, B, and C, and F and G. And then it also has a list which sends the syntax, which sends like the symbol corresponding to the generator to the actual to the index in these generator lists.
Yeah. Okay. So that arrow, that fat arrow after HOM is just pair, if I remember. Okay. That is a tricky syntax for not Julia users.
Yeah.
Okay.
And this is the syntax for indexing is overloaded. So if you do C sub F, you get F.
Cool.
Well, and it displays in LaTeX, which is not so useful. So let's dump this and see what we get.
Okay.
So we get yeah, so basically it has arguments F, and then the domain and the codomain, and then the type arguments are also the domain and the codomain. I don't entirely understand what's going on here, but you can use the accessor functions. So the domain, and we can dump this, and this is going to be an ob expression. Or yeah, just no, yeah. So main.freeCategory.ob. And then we also have codomain. So you can sort of work. So basically you can just work with these. You basically get to work with the syntax in somewhat of an intuitive way.
So can you compose that F with ID of B?
Why? Yes, you can. Oh, not code. Compose CF CG. Great. So helpful. Dump that. And you see we get a compose. And yeah, this is like some big syntax tree, but basically it's
I was more curious about can we refer to the identity morphisms even though it's not part of the presentation? I guess it came from free category, but
yes, dump ID on CA.
Cool.
And you see that the tag here, the tag, which is actually part of the type, refers to the term constructor that generated it. So unlike a general category, these categories are sort of you can decompose these categories. Every object in a free category
Mhm.
is a generator, and every HOM is either a generator, an identity, or a composition.
Mhm.
Yeah.
So that makes it easy. I mean, I think of like the reason why we like that property is that so we can define functions from, out of something. So you can say for each case, I'm going to define what happens.
Right. Right. Or like event or and actually it's even it's even better than that because the term constructor is in the type.
Mhm.
You can actually use Julia's method overload system
Ooh,
to define methods based on the term constructor,
okay.
and that's why we put it in the type.
Mhm. Cool. All right. I think I understand this, but if there's like something I should do to demonstrate my understanding, let me know. But
Yeah, do something interesting.
this is not what I mean, I already said to like do the identity here, but let's see. So I mean, maybe something interesting is like to try to break. I mean, I know that the type system is not super rigorous. Like, try to break Catlab by entering in.
Yeah, break Catlab, do it.
I mean, I'm not. Yeah, hopefully you get a good error. Let me scroll down. I've been looking at your screen. What number are we on? 31. Uh, so if I do a different presentation, but instead I do HOM ABC.
Oh yeah, let's see what happens. I have no idea what's gonna happen.
Looks like
Method error. There we go.
that's what we want.
Okay, good. Yeah, we validate that.
Why don't we define F again?
Name F already defined in presentation. So yeah,
Hey,
we're a little smart. We're a little
guys.
we're a little smart.
Uh, yeah. If we put there, that seems like should not compile.
Yeah. Yeah. Oh, and actually here you get to see that actually HOM is defined using an override.
Mm-hmm.
So HOM takes in two main.free category dot ob. So we sort of do use types. The type system does actually sometimes save our ass. Um, but yeah.
Cool. Yeah. I could try to think of other ways to break this, but no, yeah, I'm really impressed that it's catching these kinds of things.
Yeah.
Cool. So, oh, we're at the end of the notebook.
Yeah, so we're at the end of the notebook, and that was pretty much an hour. So I think that was pretty good.
Yeah.
Um, I'm realizing I probably should not have. I don't know. I guess if I was, it sort of made sense to me to keep this vertical, but I guess it doesn't really make sense that this random Emacs window is open.
Yeah.
But
I mean, but it's pretty constant if you want to like block it. I don't know. There's probably some video editing thing. You just put something over so it's not distracting.
yeah, or the audience can just ponder over this question: is the transformation between C sets and natural transformation?
Yeah, I
Is it?
didn't even look. Uh, cool.
Anyway, so let me stop recording. Yeah.